Hello there. In this lesson, we're going to learn about reaction rates. So if you've ever been camping and you've tried to light a fire, sometimes the fire will burn very quickly, light easily, and away it will go. Maybe you have nice dry wood and good tinder to use to get the fire started. And other times it can be really tough. Maybe you don't have any paper or tinder to start with, and maybe you don't have the driest wood. And so there are factors that will affect how fast reactions will go. So this unit we're going to look at factors that affect reaction rate, how chemists quantify reaction rate, and ways that we can look for patterns in the way that reactions go. So the fancy term for the speed of a reaction, how fast a reaction is going, is kinetics. You can think of like motion or the rate of reaction. And so this is generally measured in terms of a change in concentration over a change in time. And so something like this where you have a reaction happening in a solution, obviously the concentration of some component in the solution is increasing over time, and so you could use that as a way to tell how quickly the reaction is going, as long as you have a way of measuring both of those things, the concentration and the time. Sometimes you might have to use like an indirect method, like the amount of gas that's produced, and you could collect that gas, and then you can measure this, this volume here, and you'd also need time, and then you can get a rate that way, and then relate it back to the concentration of these reactants that are causing the reaction to go in the first place. Since reactions aren't all the same, you're going to have to use different methods to be able to determine how fast the reaction is going. For that reaction on the previous page where the solution was getting darker and darker, you could use one of these things, which is a spectrometer. And basically it will measure how much light can pass through a sample or how much light is absorbed, and you can use that and of course a measure of time to be able to tell the rate of the reaction. For reaction that produces gases, you could measure the pressure of gas that's produced inside of a reaction chamber, or the volume like this setup here, so that can be convenient. Some reactions involve ions that you could use a conductivity apparatus to tell the difference between different stages of the reaction. If you have acids or bases being formed, you could use a pH meter or another indicator to be able to tell how quickly those type of reactions are going. And yeah, so that's those are some options. You got volume, you got pressure, you've got conductivity and pH, and you have absorbance if it's something where the color is changing. So let's have a look at some of these reactions and see if we can imagine a way in which we can measure the rate for these. So first off, you see you have HCl here, that's an acid, hydrochloric acid. So you could use pH for this guy. You could see the rate of change of the pH over time, and that would give you a rate of reaction. We also have a gas being formed as well, so we could use pressure or volume measurements to determine how fast that reaction is going. In this next one, we have another acid here. This is nitric acid, so we could use a pH as well for that. We also have copper ions, which are blue, and so you could use your spectrometer for that. Or you could use the pressure volume thing again for gases. On the other side here, what do we have? We have a base being made, right? The base, so you could use pH for this. Again, you have a gas that's being formed, so again, pressure and volume could be used. And also, you start off with two substances that don't have ions or aren't ionic. So you've got a metal and you've got a molecule, the liquid, and these are ions, right? KOH is an ionic compound. So you could use conductivity here because the two components you had to begin with are not really conductive, and then once the reaction starts going, it would become more and more conductive as time went on. Now, whatever method you use to determine the rate of reaction, you're going to convert it eventually into a change in concentration. Concentration is measured in moles per liter, and the time is generally measured in seconds. And so the usual units are going to be moles per liter per second, which can be expressed like this. An alternate is to, instead of putting the line here, you can express it to the -1. That just means it's on the bottom as a reciprocal. So your rate then will be a change, that's what delta means, in concentration. So the square brackets are concentration of some reactant. There you go. Over the change again, so both of these mean change in the time. So for delta anything, it's always the final condition minus the initial condition. So change in concentration is final concentration minus initial concentration. And then for change in time, it's final time minus initial time. Now from your data that you collect, you can plot to show the change in reactants and products over time. So your reactants are going to be the stuff that you start with, and they get used up over time, right? So this line here represents reactants, and you see they're getting used up. And then over here you have products, and they're being formed. So here is products, and they're being formed. And so you can always tell on the graph which one's reactants and which one's products just by the way the lines are going up or down. Now, if you want the rate's going to be the slope of this line. Of course, since it's a curve, you're going to have to either work out the slope for a section of it or a tangent line, which we'll look at in a second. So first of all, if you want an average rate, so the rate of reaction over a period of time, since the reaction rate tends to be faster, you see the slope here, it's faster at the beginning and then it slows down at the end. In order to get an average, what you do is just connect any 2 points and find the slope in between. So the average from for this first section from 0 to 500 seconds would be determined using your equation. So the rate is going to be, or the average rate is going to be the change in concentration divided by the change in time. So you're going to do final time, or concentration final minus concentration initial, there we go, all over time final minus time initial. And so the final concentration is down here, it's around 0.1 moles per liter, and the initial concentration is up here, it's like 1.7 moles per liter, and the final time is the 500 seconds. Initial time was 0 seconds, so we end up with negative 1.6 moles per liter all over 500 seconds. And let's see what that comes out to on my calculator here. And so I get negative 0.0032 moles per liter per second. Instantaneous rates are found by finding the slope of a tangent. So tangent is a straight line that just touches a curve at one spot. So this is the one spot that we're going to be measuring the rate of reaction for. And so the rate of reaction will be the slope of this line. So we'll estimate, just take any 2 points along the straight line that you made here and work out, rise over run for it. So we'll make this our triangle here. So the instantaneous rate would be, same change in concentration all over change in time. So the final concentration here we have is 0.001 moles per liter, and the initial looks like 0.0045 moles per liter, and then we'll divide that by the difference in time. This looks to be about, 120 seconds, and the initial I'll say is 0. So that means 0.0045 0.0035, negative 0.0035 moles per liter divided by the 120 seconds. And so that instantaneous rate will be 0.0035 divided by 120 equals, so negative 0.123429 moles per liter per second. So there you go. You can always find the rate of reaction, either average or instantaneous, by taking the slope of either secant that touches the line at 2 points, or a tangent that touches the line just at 1 point. Okay, so a few other things here that to point out about concentration versus time graphs. One is that the concentrations are going to change according to the proportions in a balanced equation. So in this reaction we have B as a reactant, and you see it's being used up. It gets used up more quickly at the beginning and more slowly over time, just because the concentration is decreasing. And then you see that A is a product here being made. So the slope makes sense here. The slope is steep to start with, and then levels off as the reaction goes forward and slows down as reactants get used up. But also the proportions have to follow too. So as 1 unit of B gets used up, 2 units of A are being formed. And so you end up with A being basically double the concentration of the change that B undertook. So that's the two things to look for when you are making sure that your concentration versus time graph makes sense. First of all, is the slope correct? Are your reactants being used up, and are your products being formed? And then do the ratios follow? And do you get 2 parts of A for every 1 part of B? And so this one makes sense for both the shape and the quantities. So finally, a really useful tool that we're going to use a lot is called an ice table. So what you do is you use it to keep track of concentrations that are changing. So ICE stands for initial, so those are all initial concentrations that you have at the beginning of a reaction. C stands for change, how do the reactants and products change relative to each other. And E is for the endpoint. Once the reaction is over, how much do we have left in each component? So when we look here, we see that of course, the reactants here are on the left and the products are on the right. So the reactants are going to get used up, so they'll always have a negative sign that goes with them. And these products are being formed, so they're going to increase. And then the other thing that happens is that the change has to follow the stoichiometric ratio. And so this is going to decrease by 3 times some change amount. This would be 1 times whatever the change amount is, and this would be 2 times whatever the change amount is. And so using that, we can determine the unknown concentration, since we have an endpoint concentration for one of these. So we know that 2.0 minus X equals 0 moles per liter. So that means that X equals 2 moles per liter. Now that we have that, we can sub it in for the others. We know that 7.0 minus 3X equals some endpoint. And so 7 minus 3 times 2 means that you're going to have 1 mole per liter left there at the end for the hydrogen. And then over here we've got 0 plus 2x equals the endpoint. And so 0 plus 2 times 2 equals 4 moles per liter, and that gives you the amount that you're going to have left over for the ammonia at the end. Alrighty, so that's it for this lesson. We'll talk to you soon.